It's called Evo of CNNs. Should I send some other link? How does it work? Yeah, YouTube page. I got let me send it to you. So there's a YouTube link that I just sent you. Yeah, I sent you a link. In Facebook, I sent you a link. Okay. See if it is working. It says live right on the screen. Yeah, to you and Malai both I sent. Okay, one viewer. Hello, hello. Who's that? Malai. Okay, and okay. All right. I got the screen share also. I'm set. One viewer. All right. I'm gonna hang up. Yeah, it's already started. It's live now. Three viewers. Hello, everyone. We are waiting for a few more people to join. Sorry for the delay. There were some technical problems getting the live stream started. As soon as we have a few more viewers, right now we have 3 viewers. Can you guys hear me? I guess I won't hear you, so I guess okay. So some of them joined. Okay, 8 viewers. One more minute, and I'll start. All right, let's get started. Okay, is my okay, I'll start. Good evening, everyone in the Eastern Hemisphere, and good morning, everyone in the Western Hemisphere. I'm your associate professor in IDLI, Guwahati. I'll be talking about evolution of convolutional neural networks for image recognition. Excuse me. Brief introduction. My research is mainly in computational pathology. I use image processing, computer vision, and machine learning to analyze digital pathology slides. And I apply deep learning for some of these for some of these problems. So the goals of this webinar would like you guys to become familiar with the components of a CNN, a convolution neural network, and understand the problems on which CNNs are applicable and the problems on which they are not. They are not a silver bullet, but for certain types of data they work, especially image data, and I'll show you why they work well on image data. And understand the reasons behind the success of CNNs, and develop a familiarity with the ongoing advances. If there are any problems with people hearing me, I'm just quickly gonna see if there are any messages. Um, doesn't look like it, so looks like everyone is able to hear me fine. All right, so we'll keep going. So before we go into CNNs, let's quickly recap what do we mean by shallow learning versus deep learning. So let's say you have a task is that you want to recognize digits. So this is a toy problem that anyone who's starting in CNNs would want to start with. So at the bottom you see some images. These are handwritten digits. For example, you see a 7 and a 5 and a 3 and so forth. And we want to recognize them. So in deep learning, you would take these images as inputs and you would extract some features from these inputs. Many times the features that you extract are not enough to recognize complex shapes with a lot of variation. For example, there are multiple ways to write 5. Some of those 5s can look like a 6 and so forth. So you extract features of features. Once you have extracted all these features, then you use a classifier. So the color coding here in this left side of the image is that the gray stuff is the input, the features, the special things. You do not tune them. You design them. You design what features to extract. You design what features of features to extract, but you don't actually learn anything in it. Whereas the classifier, which is in the red, and I've shown those black knobs. Those knobs are the tunable weights or different parameters of a classifier. That's the only thing that it learns. So the classifier is kind of like just one layer. If you think about a support vector machine, it's a perceptron. It doesn't train like a neural network does, but it is a perceptron. It uses training. Well, it's a different kind of a loss function, but it is just one that makes a support vector machine. Contrast that with deep learning. In deep learning, you take that input and you would extract features from those inputs, features of features, and then you will learn a classifier. But the features of features, and the classifier, all of them are trainable. They all have weights that you fine tune, and that's what makes it deep. The hierarchy of learn. So can we do everything in shallow? Why do we need to go deep? Let's go with the same example. So you have images, and let's say these images in edited digits. These images are on 28 by 28. So you have 28 squared pixels. So this essentially you have a 786 dimensional vector, 28 squared vector. From that you can actually directly learn an SVM. The problem with this is that does it learn a good representation of what it means to be a digit 7 or a digit 6? And many times it does not, because it does not the vectors for two images that both have 7 can be remarkably different just if the digit 7 translates a little bit, scales a little bit, or in colored images if there's a slight color change. And the underlying shape or the stroke of the pen strokes, those remain, yet the vector of like just the pixels can be very different. And in fact, two vectors of two different classes, like a 6 and a 5, can actually be very close to each other. SVM would have a difficult time telling them apart. So that's why you don't get very high accuracy with even such a simple task using a shallow layer. On the other hand, using deep hierarchy of features even when there was no deep learning. So people were not feeding pixels directly into a classifier. They were extracting points and then features of features like histogram of interest points and then classifiers. So those things keep building deep hierarchies, except that the 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 depths were not learning, only the learning. So is there a way to make this hierarchy and actually in a principled way learn the parameters in the hierarchy itself? That's what deep learning is all about. So enter neural networks, and in neural networks, what you have is you have an input layer, and you have multiple layers of neurons. You have several and output layer at the top. Um, so these different hidden layers, the first hidden layer basically transforms the input into some set of features. And the next hidden layer, I have shown only one hidden layer here, but there could be multiple hidden layers. These layers would extract like features of features, like they will form transforms of the transforms of input and so forth until you reach the output. So each neuron here is doing a simple task. It's a nonlinear function applied to a linear combination of its input. So that's what the equation at the bottom shows. And the way these neural networks are usually structured is that this neuron was only connected to neurons in the previous layer. Not, it doesn't skip layers. It is not connected to neurons above it. It does or like two steps below it or so forth, two levels below it. So the question is, each of these weights, each of these connections that basically show where the input flows from one neuron to another. The question is, the weights on these lines, how should we tune them? So it's basically a credit assignment problem. Let's look at this yk, and let's assume that there is some error. It's not the right label, the class label that you desire. In that case, what you would want to do is you would want to compute an error or loss function, and you want to propagate it back to the hidden layers. Now, if there are multiple hidden layers, okay, then it goes to like nodes of those hidden layers and then to the ones below that and so forth. Ultimately, what happens is uh, there are just too many paths to any hidden neuron from the output layer that the gradient, the gradient that is, yeah, error gradient that is sent ends up getting very diluted. It is not very how shall I put it? It does not. It has like high entropy. It is not like very peaky. So it doesn't. Neurons tend change their weights simultaneously and so forth. So it was very difficult before convolution neural networks to actually tune these weights. So here's an example of a three hidden layer neural network. So now you can see it's a jungle of these, and if you pick, let's say, some neuron in the first hidden layer from the bottom, and see how much it contributes to the error at the output. So many paths to it that it's very difficult to pinpoint how the weights that are coming into the input should be tuned. So the error gets very dense, etc. So we need to control this architecture. If you look at any two pairs of layers, there is, so let's say if there are n neurons in each layer, then there's n square number of layers, any two consecutive layers, times the number of layers. So that's a lot of connections. So how do we control this architecture so that you can have a lot of layers and you don't have this square explosion times number of layers explosion in the numbers that you need to tune or the weights that you need to tune. So what if we share some weights? So let me give you an example. So if you look at this particular neuron and look at the three weights that are connected to it, actually there are more than these three. How it is to the neurons in the previous layer. One of the weights I've shown in red, the other in blue, and the third in green. Now, let's assume that I constrain that the next neuron has exactly the same weight in the relative positions when it connects to the previous layer. So something like this. So in this case, the next neuron will also be connected with the same weight to the neuron two steps to its left, with the same weight to the neuron one step to its weight to the neuron at the bottom. So this pattern keeps repeating. So when you have a set of weights and you move it around and they stay the same, in signal processing, this operation is known as convolution. That's where the convolution neural networks comes in. So here's an example of how convolution works. So here you see the black signal. That's the triangular black signal. You have this green signal, which is a set of weights that just keeps translating over it. And then you take a point-wise product and then you sum it up. So sum product, and what you get is the output, which is the red below. So this translation, where the weight or the kernel that you are multiplying it stays the same in shape and moves across it, is called convolution. Now, this can also be done in two dimensions, which is how it is done in images. So here you have a big matrix on the left with the numbers 7, 6, 5, 5, 6, 7. Let's say those are the images. And the matrix at in the middle with these numbers -1, 0, -1, 0, and -1, 5. Sorry, -2, -1, 5, -1, etc. That's a kernel. So that lays on top of the matrix. There's a sum product operation that goes on, and the sum product is put in the output that is on the right side. Pixel does the same operation and shifts. So you see the kernel, the 3 by 3 matrix solving over the previous matrix, that does not change its shape. Now, if you think about two consecutive layers that are in a shape of a square, so because they're modeling like an image two-dimensional grid, and they both have, let's say, 6 by 6, their size is 6x. If they were fully connected, unlike the previous type of neural networks that people were used to, there will be 6 to the power 4 different connections. But if you were doing only convolution, it will not change, and you would need only 3 by 3. For this kind of why does it? So the convolution kernel, this 3 by 3 matrix that you see, is sort of a matched filter. What it does is it gives you the maximum output, assuming that all the weights sum up to 0. Output when the relative when the part of the image on which it is convolving at that particular has the same set of relative values. The spatial distribution is is relatively the same as that of the kernel. So whatever shape is in the kernel, it is looking for that shape in the image or in the previous layer. So that's called a matched filter. So you will see in convolutional neural networks that when you know convolutional weights, they edges, because that those are the features that they're looking for. If you're looking, trying to recognize a cat and you're trying to recognize its ears, then you will have the edges of the ear at certain angles, and the first layer of convolutional weights will be looking for edges of that orientation. But the good thing is that you don't have to specify what to extract. So these patterns have to be ergodic. So what I mean by ergodic is that there are certain reusable patterns that can appear anywhere in the image. So if you're looking for vertical edges, you're not really at one, you're looking for vertical edges that could be anywhere. So reusable feature that you are looking for in different places. So that's an ergodic signal that can have the same characteristics at different places. And when you are looking for that, those reusable filters, then you can, it makes the feature detection more efficient. You don't have to build separate edge orientation detectors at each point in the image. You can use the same set of filters and just convolve it all over the image. So the first CNN actually came in the late 80s. and early 2000s, and he showed that for handwritten digits they did really well, better than any other methods that were there at that time. And it was a very simple architecture. It had followed by a subsampling pooling, one subsampling, etc., and then so basically two conv layers and then a set of fully connected layers. And this did remarkably well. So when we saw it in the late 90s, people, my contemporaries who were doing research at the time, we were all very excited. We all knew that we need to hand specific features to be extracted is not going to be a good. We need to actually learn these. It will be nice to learn these filters, but it was very challenging to code the CNNs at that time. There was no Theano, and to train it could take like days, or days is maybe more, weeks, because GPU optimization for CNNs had not come in. But it was an exciting idea. It was exciting idea of its time, and then of course later it exploded. So what we gain by using a convolution layer is, let's take an example of that is of the size 28 by 28 by 25, and the input is of the size 30. How much number of weights we can save, how much the number of total we can save. So let's say there's a color image of 32, and because it has three channels RGB, it is 32 by 32 by 3, and you want to extract 25 different layers, 25 different set of features from it in the first layer. So let's say these features are of the size 5 by 5. So you want to extract 28 by 28 by 25. Now, uh, so if you want to do this and you want to have a filter that is specific to each location, then you would input in a hidden layer. So which is 32 by 32 by 30 by 3 times 28 by 28 by 25. So that's like connections. But if you say I want to extract this set of features by using just the same set of kernels just applied to different locations, then the number of weights that you will use for a 5 by 5 filter would be 5 by 5 by 3 to take the 3-layer input, and then you have these for the 25 different types of features, but the same features at different places. So it's only 1875 weights as opposed to 60 million weights. So that's what you gain. Now, the other thing that it does weight in terms of so when you reduce these weights, you can increase the number of layers per hierarchies. The other thing it does is it forces detection of the same features at different places. In that, it actually has a very powerful regularizing effect. So as you know from regularization is very important, so that you don't have in machine learning. So all this is good, but what are convolutions good for, and why on what kind of data they're not good for? Data that comes on a grid. So there has to be some temporal order or a spatial order or something. So they're good for speech, they're good for text. You can use it for protein structures, DNA structures, for images. Now, protein and DNA structures that I mentioned here, or that I mentioned here, now they have, people don't use CNNs anymore. They use LSTMs, but before LSTMs, CNNs could have also been used. They would have been better than any or other kind of models that were used. So the order of data elements is important. Only then convolutions are useful. Uh, for certain other kinds of data, let's say if you have a data vector, and if you permute dimensions of that vector, and the meaning of the vector doesn't change, convolutions are not the right way to analyze it. So for example, there's a famous breast set where you have patient factors like age, whether she was a smoker, whether she was a drink, she used to drink, whether she breastfed her kids, whether she had BRCA1 mutation and so forth. So in this case, if you permute these dimensions, you can get a very Hello, can you hear me? Sorry, I just had a power failure. Is everyone, can everyone hear me? I was saying that so when you cannot jumble the pixels of an image and still expect it to be so the next step is pooling. Pooling does in a convolution neural net, it reduces of the feature map that you have just computed, and it does this by local averaging or taking local max. So it does a couple of things. One, it reduces the size of the feature map on which the next layer will work. The second thing it does is that it lends a bit of translation invariance to the features that have been detected. So, for example, if you look at this number 6, it's the largest number in its neighborhood, and let's say it came from some feature detector, one of the kernels of the previous convolution layer. All that matters is whether it has been detected or not, and whether it is detected in this place or slightly to the left pixel or the up pixel or the down pixel, that doesn't matter. Find whether it has been detected or not, and that's what the max pooling does. So, and the last few layers are just fully connected, just like a regular neural network or a that gives you the classification of the convolution. All that works good. It's pretty good. And then do that does a structure of convolution prediction, causing effect on this error backpropagation. And the pooling, mind you, doesn't have anything to tune. There's nothing to tune there. There are no weights there. Okay. So this brings me to the second part of the talk, where I'm going to talk about improvements to this basic CNN architecture that has been going on and the training that takes place. So the first improvement that came along was the use of max pooling instead of average pooling, and the logic behind this was, if you look at a cluster of four numbers, right, and let's say these are the features detected by the previous convolutional layer. So the large numbers actually tell you whether the feature was detected or not, assuming that the non-linearity there was a RealOO or some sort of a positive non-linearity. And what average pooling would do is kind of blur the detection of that over compare that to max will only find the strong presence of the feature because it will look at only the max in the area that it will pool over. So this pooling, some are giving translation invariance. The average pooling is diffusing the features to some extent. Max pooling is detecting strong presence of features. Next improvement that came about was non, and you take a sum product of the previous of its inputs. Non-linearity has to be applied. If you don't apply a non-linearity, it doesn't really work very well. It actually it becomes like a whole giant linear function, which is not what you want. Non-linearity is its strength. So in theory, you can actually use any nonlinear function for the squashing function. And earlier people used to use sigmoid or tanh. But RealOO has been used in the recent past. It has been is being used in the recent past. One of the reasons why RealOO is used, basically its gradient is one. Um, so it doesn't have, compared to tanh or sigmoid, that have flat tails on both ends. It doesn't have a zero gradient on. It has zero gradient on only one side. So it has a more chance of actually tuning the weights that are behind it, because it does not have that vanishing gradient problem. always stays one on one side of it. One of this another pretty standard technique these days in training your CNNs is using dropout. If you look at this neural network on a network, I'm just using an example of a fully connected network, not showing convolutions here. So if you look at that, you have all the neurons that are present there, but when you are training them using dropout, you will pick the ones that are crossed out in the right set of neurons that you will completely drop out. So all connections going in and out of those neurons will not exist. And this is done for pick a different set of neurons to drop. So when two neurons are always present, they errors of one can be compensated by negative errors of the other. And what that does is it kind of makes them co-adapt. But with dropout, what you are trying to do is you are trying to break that co-adaptation so that each neuron learns an independent set of features. So they learn features that are sparse and kind of like a dirty way of enforcing sparse coding. It's also an equivalent of adding random noise. Adding random noise makes learning more robust. If you can learn is and you can still perform well, probably perform well on the test data. It kind of drop out a few neurons, you're training a different neural network. So it's basically training some order 2 to the power n being the number of neurons, neural networks in one neuron. So you're doing a dirty average of it. So it's not Bayesian averaging, which would have been much better. But practically, this works pretty well. The next set of improvements came in training, in the training algorithm. So one most widely used was using mean squared error. So that for classification problems, usually it's not being used. It's only used for regression problems now. People use much more well suited such as cross entropy loss or something like that. And then there's weight decay. So basically, magnitude of it itself so that they don't become too large. You would put some sort of an adaptive rate using momentum, and you would also the overall learning rate so that whenever the performance saturates, usually it means that you are taking too large of steps, so you reduce the step size dramatically, not using momentum but like using another procedure. So there are various fancy momentum procedures and adaptive learning available now at a grad and so forth. So you can check those out. The next set of improvements come. I mean, I would this by meme. So if you who know me know that I'm a meme enthusiast. We need to go deeper. This is from Inception. That's how the Inception module of the Google Net was also named. So basically, we need to increase the layers dramatically, much more. So how do we do that? So there were a couple of new suggestions that came from starting at VGGNet. So in VGGNet, this was the first time people went like as deep as AlexNet, which was just slightly like twice as deep as LayNet, for example. So in this case, the way the author suggested going deeper was large convolutional filters. No 7 by 7s, no 9 by 9s, no, not even 5 by 5s, filters. So now you're reducing. So every time you go from 7 to 5 to 3, you are reducing the number of weights by n squared, so 3 squared, right? So you are for each layer you're using very few weights, but now you can increase the number of layers. So you can do more layers. So VGG had 19 layers, they 19 layers to experiment with the ImageNet data, and they got very fantastic results. Uh, Another set of innovations came from GoogleNet, uh, where they also standardizing the convolutional filter size. They used convolution layers and 5 by 5 and 1 by 1. So they had a couple of innovations in this architecture. What they did was, one, they used small convolutions just like VGGNet, but they also brought in this idea of convolution filter. If you think about it, what does 1 by 1 convolution even mean? I mean, it is not detecting any spatial structure, right? To detect any shape, you need to have at least a 3 by 3 to look what's around a pixel. What 1 by 1 does, it does sort of a dimensionality reduction and adds some linearity. So what matters is what is the depth input it is taking and what is the depth output it is giving. So that gives dimensionality reduction. And so if you look at these 3 by 3 and the 5 by 5, they were 1 by 1 that did dimensionality reduction for them. So the previous layer go to a 1 by 1 and then going to like 3 by 3 and a 5 by 5. And all these filters will be concatenated for the next one. The other thing they introduced was something called a companion loss function. What that means, um, so you have to tilt your head a little bit for this slide. If you tilt your head a little bit to the left and the output is on the right, it's not going from bottom to top, it's going from left to right, because I could not fit it on one slide if I had kept it vertical. Now, look at the number of layers that it has. It has 20 layers or more, comparable to VGGNet and like slightly more. So, whenever you have a large number of layers, remember we need to go deeper because that's where we think the gains are going to be. The layers that are close to the output, they are getting direct feed of the error gradient to tune them. And the layers that are close to the input, they are going to learn the basic image features like edge oriented. It's the layers in the middle that find it hard to adapt. So what they did was they gave error gradient not only to the from the error of the output to the final layers, but they included some gradient towards the middle layers. That's only for training uh, at some point in the training, in the few iterations of the training. Once you have learned a good number of features, then these were removed. So it's called a companion loss function. I don't think GoogleNet used the term companion loss function, but in some other that term has been used. Okay. Then a dramatic shift came in how these convolution rails are organized when the residual nets came. Now um, think of a stack of two convolutional layers, right? So whenever you add more layers in a neural network, you how is it training error? It does worse. After a certain number of depth, adding more layers is detrimental for even training error. So to some researchers. Why can't two layers that are added not do simple thing? The problem why they cannot do is because they they have random initialization of weights, and that random initialization of weights already gets stuck in certain function directed models. They want it to make it easy to model identity functions such that if you add a few more layers, it should do at least as good as a shallower model, as a shallower neural network. Then what you have to do is you have to add a bypass connection to the identity function such that the layers in between are garbage or their weights are at least you will do as good as if these layers didn't exist at all. So this connection was basically model the residual of the error as opposed to the error itself, or residual of whatever the incoming signal was as opposed to the signal itself. So now you could add more layers, and now they could add many more layers. So in fact, when this paper came out, they experimented with like 30 layers, 50 layers, 100 layers even, which was unprecedented before residual net. Before that, Google Net had only 22 layers, VGG Net has 19 layers. So dramatically, they went to from 19 or 22 layers to 50 layers and even 100 layers. Found that usually 50 or 100 layers were good enough for ImageNet. So this is an architecture that shows many layers using these bypass connections, which are model the residual. Now it has become pretty much standard to use residual nets. So these are the set of innovations that CNNs in the recent past. And basically, what I want to end this webinar by saying is that deep learning is actually not difficult at all. It's pretty easy. It is fast becoming a commodity. If you get a hang of how different architectures work a certain way, what are the new innovations that are coming, you have an access to a GPU that can implement CUDA, that can run CUDA. You can always even rent G2 instances on AWS. You don't even have to buy your own machine. Then it is very easy. Like there are libraries that are very easy to work with, Theano and Keras. Theano is a little bit more difficult, but Keras that works on top of Node.js, that works on even on top of TensorFlow. It's very easy. I'll show you a code snippet very shortly. You can go to GitHub and find like even pre-trained weights to start with, so that you just fine tune the weights. You don't even have to learn the weights from scratch. So it is becoming quite easy, and I interested in object classification to give deep learning or CNNs a try. So here's a code snippet. So this is Keras. What you'll see here is all you do is like tell what the batch sizes, number of classes, how many epochs to run, what is your different layer sizes, what kind of what size of you want to use, and then you just basically so here you have some data and you're adding a convolutional layer, you are adding an activation of RealOO, another convolution layer, dropout, then your flatten layer, basically the flatten for dense layers and so forth. After that, you just compile the model, and then you basically that will do the evaluation. That's all there is to it. It's like it's as easy as it gets with Keras kind of libraries or Torch. It has become very easy now. So the takeaways are that for images, text, and audio, CNNs are not just a fad; they are here to stay. They are the other shallower models, SVMs or whatever that were there before that, are not coming back. If they come back, they will be in combination with a deep hierarchy of learned features using CNN, unless like something better comes about. Their performance is comprehensively better, especially when you have data where the order matters and the amount of data is large. That's one thing to keep in mind. You need data to train CNNs. You cannot do that on a few thousand images. You need tens of thousands, hundreds of thousands of images to train CNN, and the data should example. Getting easy, code and even weights are available, so you can go ahead and give it a whirl. Go forth and convolve. That's it for my seminar. If you have any questions, I can take that. You can maybe type in the chat box. Can you talk weight decay and momentum? Uh, sure. So weight decay is basically an L2 penalty on the weights. So basically, whenever the weights become too high, the L2 penalty will try to shrink them. So that's what weight decay is. It's a standard regularization technique that you would use, for example, in logistic regression. It's just the L2 penalty that the term is called weight decay in numerical parlance. And momentum is about basically learning rate change, depending on your error decreasing. So usually, if your error increases, like if you think of a paraboloid of loss function and your loss function increases, that means you took too large of a step, and basically you look at two previous steps to figure out whether it was a large step and reduce the step size adaptively. So that is momentum. So it's kind of like adding a momentum to a ball that's trying to find the local minima. Okay, let's see. Jacob had a question. Um, where are CNNs used besides images and how? So, like I mentioned, anytime you have data that has an order and a local structure is appear anywhere in that order on a grid. So that could be, for example, phonemes of speech. So for speech recognition, for finding events in a video or activities in a video, you could use a CNN. Your sequence of amino acid sequences that you can find anywhere in the of a protein, the primary structure, then you could use a CNN. So there have been some papers using CNNs in protein structures, but not anymore. Now people use LSTMs, but you could use CNNs there also. So anytime you have either one-dimensional, two-dimensional, three-dimensional structure, so three-dimensional could be even an MRI, finding a particular tumor and like certain blood flow patterns that could appear anywhere. For that, you could use a CNN. Could you touch on sparsity principles for CNN? So basically what you want is when you have a set of that are detecting different features at different places in the previous input layer, in the previous layer. Uh, you want at any given location, you want only one feature to be detected, not all features. So think about it this way. If you're looking for faces, at some point you would have either the eye or the nose, but not both. So that is sparsity. You would have only one feature or the other. So we don't code an eye detector or a nose detector in CNN. CNN learns on its own, and let's say they correspond to an eye detection and a nose detection. At a particular given location, only one of them will give you high response, the others will not give you high response. So that is it will of the all feature detectors that were available only give you high response. So so such sparseness is useful in many learning problems. In CNNs, you don't actually use like an L1 norm to enforce sparseness. The sparseness comes from things like dropout, where you are saying that, okay, I'm not going to only train one type of a detector in this iteration and another type of detector in this iteration and so forth, and it will naturally come out to be sparse. In fact, um, because detectors are sort of like object or local structure detectors, they tend to be sparse naturally. Uh, there's also a conv LSTM. How is it related to CNN? So I am not completely sure that you have an LSTM structure and you are convolving that structure over the entire image grid. What it does is it's because of convolution, its weights remain the same wherever it is applied. But the LSTM part is that it still has a local memory that retains what it has processed, before that in the sequence it was applied. So it combines the best of both. All right. Looks like that's it. And right on time. Thank you very much. This was a pleasure. I hope you guys enjoyed the session. Sorry for the issues, but continue such sessions. Thank you very much. Good night to people on the Eastern Hemisphere and good morning to people on the Western Hemisphere. Thank you.